So now that we've reviewed and learned a little bit more about univariate regression, we're going to talk about multivariate multiple regression. And we'll talk a little bit more about this next week as well. So multivariate regression isn't quite as common as MANOVA, but now that we have our matrix notation, we can pretty easily just write several multiple regressions as a single multivariate multiple regression. We just extend out our n by 1 vector of y's for our response variable into an n by m matrix, where m is the number of response variables. So now our y's are going to have multiple columns. And our design matrix Z stays exactly the same as what we saw. It's still just a column of ones and then all of our predictor variables. And our beta matrix becomes p plus 1 by m instead of p plus 1 by 1. And our residuals become n by m instead of n by 1. So having expanded out our y, beta, and e matrices, epsilon to accommodate the multiple response variables, our actual matrix multiple regression equation stays exactly the same. It's y equals zb plus epsilon. So what we're just saying here is that this formula we have m separate univariate multiple regressions for each of our response variables, each of which has the same set of predictor variables at the same time. So on their own, multivariate regression models aren't as immediately informative as their individual univariate counterparts or their components. So where they do have some utility is in making simultaneous inferences about predictors on multiple response variables. So because our residuals are now m by n, so when we do E transpose E, this is no longer just the sums of squares, but it's a full sums of squares and cross products. And so what does this imply? What does having cross products for our residuals imply that is different from the separate univariate regressions? So it implies that the residuals might be correlated across the different response variables. So this is the extra information that we can test is whether the predictor variables also predict the correlation in the residuals or the correlation in the response variables. So we can simultaneously compare the effect of one or more predictors on more than one response variables by comparing the E matrix, which is just the SSCP from the full model, to the H matrix, which is the SSCP reduced model minus the SSCP full model. So it's the change in sums of squares. It's how much the sums of squares are reduced in the full model, or the sums of squares and cross products. And so using the lambda statistic, we can test this as the determinant of E divided by the determinant of E plus H, or the sums of squares cross products full divided by the sums of squares cross products reduced, the determinants of it. So building on our multiple regression using runs, ERA, and defense to predict wins, we simply add the second response variable in here. And so we can estimate the model as we've seen just by C-binding the response variables and then having our predictors on the right-hand side, just like in a standard regression equation. And it gives us the summary output for this MLM object is going to actually give us just two separate LMs. So it's going to give us the summary output for the regular model that we've already seen with the outcome variable being wins, the response variable being wins. And then it's also going to give us a separate one for attendance. So here is the summary output for attendance. So the summary output for the multivariate linear regression is just going to list both of these. So it's going to give us the separate linear regressions. And so do we notice anything sort of interesting about this result? So even though it had very little effect on wins in our last slide deck, defense seems to actually predict attendance above and beyond runs and ERA. But each of these outputs is just part of the picture. So now let's see if defense predicts wins and attendance simultaneously. So first, we're going to get the residuals with the resid function like we've seen. So this is now two sets of residuals. So it's the residuals for wins and the residuals for attendance from each separate multivariate or each separate multiple regression. And so I can transpose and multiply the residuals by themselves to get the SSCP. And so this is from the full model. So now I'm going to do the same thing for a reduced model where I delete defense. And so now I get my SSCP for the reduced model. So the E matrix is simply the SSCP full, but H is the difference between SSCP reduced and SSCP full. So here I'm going to create the new H object. And then we get lambda as determinant of E divided by the determinant of E plus H. Or we could just get lambda as the determinant of the full SSCP divided by the reduced. And the reason I went through this extra step is because the big A ANOVA output in R gives us the hypothesis matrix here, the H, instead of the full and reduced. So it's good to know where these come from. So the book provides a chi-square approximation for lambda that works in large samples, but we can also get an exact F. The confusing part about F, as we've seen in other cases, is that it depends on how many variables you have on both sides of the equation, so how many predictors and response variables. The book doesn't actually seem to have a table for the F distribution for this stuff, but it is what R gives us. So don't worry too much about how you're converting this lambda to an F or getting the degrees of freedom. Just understand that this is the interpretation of the R output is that these are F statistics. And of course, the big A ANOVA will give us a much larger output. So you can see just the top of it here. It's going to give you all the other, the Pillai's trace and the Roy's largest root. And so it's going to give you all the statistics that you might test. And it's also going to give you the SSCP for error and the SSCP for the hypothesis for each predictor variable, one at a time. So here our conclusion is the effect of defense on wins and attendance simultaneously above and beyond runs in ERA was significant. There's our lambda, our F, and our P. And so this is from this bottom row of the table down here is where I got this from. And of course, we can compare any nested models we'd like. So here I'm going to fit a reduced model that just has runs, doesn't have pitching or defense, and to check the simultaneous effect of defense and ERA on wins above and beyond runs. Then I compare the reduced to the full, and that gives me my F test for multiple predictors at the same time on multiple responses. And so there's the interpretation.